You're muted.
You're muted, Fabian.
Yes, thanks. Um, let's see. Can you see this now? Sorry about this.
Yes.
Okay, so yeah, it's great to be here and listen to both of these workshops. Yeah, so what we'll talk about is a bit on an interface between these two. Although to be fair, I will not address so much the field theory aspect, although it is there just simply because I only have 35 minutes and it was just too much to cover. So I focused instead on making this talk as accessible as possible to everyone here, rather than targeting to really only a small subset of people. Okay, so it's a little slow, but okay, so right. So what's the big problem with large-scale structure compared to the CMB is that unlike the CMB, every data point that we collect is highly nonlinear, is the result of a very complex nonlinear and non-local process, unlike the CMB, where we really measure small perturbations to a distribution function that is close to equilibrium. So I think we should be happy that we can get any information robustly out of large-scale structure, because it's really a very, very difficult thing to do. So 2 points that I wanted to address in this. First, I think I'm trying to convince you, if you're not already convinced of this, that there's much more trustable information in galaxy clustering than what we are using so far. So I'm going to focus on galaxy clustering, although in principle, a lot of this also applies to galaxy shape correlations used in lensing. And then second, that we can deal with these complexities, these nonlinearities that I mentioned rigorously if we restrict to galaxy clustering on large scales. So how do we compare our theory for galaxy clustering with the data in the first place? This is related to the question of small perturbations and linear theory, because we know that the primordial fluctuations are close to Gaussian. So if we have a field that is linear, then that will also be close to Gaussian. And if we're dealing with a Gaussian random field, here I'm using this terminology as we always do in cosmology. A Gaussian field is one whose PDF is a multivariate Gaussian with a diagonal covariance in Fourier space. Then all the information is contained in the power spectrum. So I can immediately compress my data to the power spectrum and deal with this one quantity that is the simplest case, where we even ignore redshift space distortion. It's really a function of the magnitude of the wave number only. And of course, this has been exploited to a great deal in galaxy surveys such as BOSS. So this is from a fairly recent BOSS result, not eBOSS. But of course, the actual galaxy density field is not Gaussian. That does not prevent us from using the power spectrum. We can still compress the data in that way, but things get more complicated in the interpretation, because this is now the power spectrum of a non-Gaussian field. And in particular, if we are thinking of galaxy clustering, we have to add bias parameters to trust the prediction once we go into the regime where nonlinear effects become important. So just as an example, again, neglecting redshift space distortions, if I go beyond the leading order power spectrum, which is linear theory, then I need 5 additional parameters. And those lead to additional contributions, which one can compute in perturbation theory. And as you can see here, which shows the fractional size of these contributions, they have very similar shapes. Okay, so there's a lot of degeneracies there that have of different terms that have smooth shapes. And the fact that we have to allow for these nuisance parameters that we don't know how to predict means that there's a limited amount of cosmological information that is available in the power spectrum by itself. So let me elaborate on this a little bit. So once you go beyond linear order, the galaxy density field has multiple terms with 3 bias coefficients that we have to include, but it also has some terms that we know how to predict. And those are precisely those terms that correspond to just the galaxy density moving with the matter on large scales. So the large scale motion of galaxies and matter has to be the same by way of the equivalence principle, because on large scales, only gravity is relevant, and gravity is the same for galaxies and for matter. And that leads to these displacement terms whose coefficients are protected by the equivalence principle. They cannot have arbitrary free bias coefficients. And that, for example, allows at second order already for disentangling between linear bias and amplitude fluctuations. So one would say, fine, okay, so we need these second order contributions. In the power spectrum, if we go to one loop order, I have these second order contributions. Yes, but they are mixed in with all these other terms that look exactly the same. So you will not be able to actually measure this independently. So, but if we go to the bispectrum, which has, not just one wave number of k, but a complex, range of kinematics you can access, then you can actually isolate this term because it has kind of a dipolar-like structure, whereas all the terms due to local non-gravitational physics are either monopoles or quadrupoles. Okay, so then you can disentangle it. And so it's very simple motivation. If we want to disentangle, if we want to get sigma 8 itself from galaxy clustering, we have to look at the bispectrum. So I should mention that the bispectrum is not the only approach. It's, from the theory side, probably the most well-defined, well-motivated approach to go beyond the power spectrum, but it has its own issues. A complicated data vector due to this kinematic configurations, a very complicated covariance. So there is a reason why there's still no full biospectrum measurement from galaxy clustering that is, has led to cosmological constraints, because it's a difficult business. And then, one could argue, well, even if I do all this work for the biospectrum, will I ever be able to go to the 4-point function? Probably not, right? It's so much more effort. I mean, it's exponentially more difficult as I go to higher endpoint functions. So a lot of people have begun studying an alternative, which is basically nonlinear transformations of the data and before doing the compression. Okay, again, so all of these are data compression algorithms that we're talking about. And one thing you can do is, before you compress the data, you do a nonlinear transformation on it. And a well-known example is BAO reconstruction, but voids, density split statistics, Mark correlation functions, Minkowski functionals, all of which people here, the audience, work on, are, of course, also all examples of this sort. So the question that this raises to me is, can we get all the information at once rather than having to look at all these things, right? I mean, I'm sure all of these have independent information, but they're clearly not all independent. So imagine having to construct the covariance between all of these different elements of the data vector. It will probably be very, very complicated. So is there an alternative? And I think there is, and I think it's anyway nice to go back to the basics of this whole cosmology inference problem that we have at our hands. So what can we really predict, right? What does our cosmological model give us? Well, if I assume a certain inflationary model or model of the early universe, I have a prediction for the statistics of the initial conditions. For example, Gaussian adiabatic initial conditions with almost scale-free power spectrum. And I can compute how a given initial density field evolves into the final density field, right? Those are the two things I know how to do given my knowledge of physics. So the first element here is nothing but a prior on the initial conditions, right? No theory of the early universe attempts to predict precisely where the curvature perturbation is positive and where it is negative. It just predicts the correlators, the statistics, right? So we have a prior on the initial conditions, but then we have a deterministic evolution into the final density field, because all the processes entering there are basically, on the scales that we're looking at, are deterministic. So it's then straightforward to formally write down the posterior of the full posterior of the cosmological parameters given the data without any compression. So this is the probability of finding a given galaxy density field, probability of finding an observed galaxy density field given a forward evolved matter density field multiplied by the prior. Both of these depend on cosmological parameters, theta, and the whole thing marginalized over the initial conditions, which we don't know, right? We only have a prior on them. Right, so this is the full posterior. This is Bayes' theorem and nothing, or not even, yeah, I mean, I guess Bayes' theorem or Bayesian inference. What is this conditional probability here? Well, I already mentioned there will be some nuisance parameters. So it's an integral over these nuisance parameters times the likelihood of finding the galaxy density field given a matter density field, given cosmological parameters, given a set of bias parameters or other nuisance coefficients. So all the physics enters here. And of course in the forward model, but that is the part we know. We know how to run an n-body simulation, for example, or to run CAMP. The prior is fortunately much easier. It's just, if you neglect primordial non-Gaussianity for the moment, then it's just a multivariate Gaussian with a diagonal covariance in Fourier space. Downside of this, and this is why no one has, we're not talking about doing this every day, is that this is of course a very high dimensional integral. I mean, formally, if you don't put any grid, any regularization, this is an infinite dimensional integral, right? So this is clearly a very difficult thing to compute. And we can basically only compute it in the case where the integrand is an exponential of a quadratic function, so a Gaussian, then we can do this integral and see that the power spectrum contains all the information. But in any other case, we cannot do this integral analytically. Still kind of confused why the slides sometimes advance and sometimes not. Anyway, so how would one do this though in principle? If you can't do it analytically, the standard approach to evaluating high dimensional integrals is our Markov chain methods. So basically you discretize all the fields on grids so that you first of all have a finite number of independent degrees of freedom. And the choice of grid resolution is of course a very important one, and we'll get back to that. Then you draw initial conditions from the prior. That's easy to do. You forward evolve using gravity, compute the likelihood, and repeat the whole thing. And so the only thing you have to worry about now is now you're sampling whatever 10 million dimensional parameter space. So this will not you will not get very far if you're just doing random walks. That's clear. So you have to do something smarter. But fortunately, techniques have been developed. And in our case, we're adopting what's called Hamiltonian Monte Carlo, which is a beautiful technique, but I won't have time to describe how it works. But I mean, we're not the only ones doing this. There's actually a whole number of people who have been pursuing an approach of this sort recently. So just as a flow chart that I made, maybe it's more clear this way. So you start with the prior, you forward evolve, then you compute the bias terms, you compute the likelihood, you sample bias parameters, and you sample the whole phases. That's basically the sampling chain that we're looking at. So this is an example of a work that came out in 2019. Guillaume Lavaux, Jens Jeschke, and Florent Leclerc did this, applied actually fairly simple likelihood to real data, to the SDSS CMAS samples, and went ahead and sampled the density field. And you can see on the right the final density field, and on the left the initial density field. It probably doesn't come out very well on Zoom with the lag, but what you can see here in the final density field is that the data are constraining, basically, are constraining the density field here, and whereas outside the region of the data, the density field is just randomly sampled from the prior because we don't have any constraints. So then we want to, in addition, sample cosmological parameters, which they did not attempt to do. So let me now get to the heart of the issue, basically. If you want to take this approach seriously, again, the nice thing is we don't have any compression. We get all the information in the data at once. But of course, we need this likelihood, right? We need to be able to say what's the likelihood of a given observed galaxy density field given the matter density field and some nuisance coefficients. If you don't get this likelihood right, then you in general expect a biased inference of both the initial conditions and cosmology. I think that's pretty obvious. And my student Min Nguyen led a study on this recently and found that indeed the amplitude of the initial conditions is biased if your likelihood is inadequate. So he tested this on halos in simulations. But interestingly, the correlation coefficient between true and reconstruct initial conditions is fairly robust. So that means if you want to use the result of this inference just for cross-correlation studies, then it's okay to use an imperfect likelihood, but certainly not if you wanted to do cosmology inference. So basically then, following the outline of the talk in the beginning, the clear question is there a way to obtain a likelihood that rigorously marginalizes the small-scale nonlinearities? And clearly, we are doing some marginalization always because we only keep a finite resolution of the grid, right? So we obviously are integrating out modes. So then the question is, how can we rigorously incorporate the effect of the modes that we're integrating out? And this is a classic example of where you would want to use an effective field theory, and in our case, the effective field theory large-scale structure. I'm not going to, well, I'm going to present the theory in the way I understand it, kind of physically in terms of intuition. I'm not going to do any formal derivations on this, but it can all be made rigorous. So yeah, so how do we do this? The perturbations in our universe are such that they are small on large scales, the density perturbations. So perturbation theory works on sufficiently large scales. So here's a plot stolen from a book that recently appeared that shows the variance of matter fluctuations per logarithmic k interval. Right? And you can see that at low k, the variance is small. At high k, it becomes large. And the different lines show different redshifts. So at higher redshifts, the whole thing is lower because of the scale-independent linear growth. And so there's a scale at which this crosses unity, and that's the scale where density fluctuations are large, and we certainly cannot believe perturbation theory. So, and on the scales where density fluctuations become large, that's also where eventually galaxy formation happens, right? So, and that's where even an n-body simulation would not be able to help us, right? We really need star formation, feedback, and all that. So the idea is to basically put in a scale that's below the nonlinear scale, put a cutoff here, and only attempt to describe the effect of the modes that are below that cutoff, right? And that cutoff lambda is something that you can think of it as a k max. This is something that is a parameter we put in, and our results should not depend on it, right? So in the end, we should vary lambda and see that the results do not depend on this lambda. So then we do the straightforward thing. We split perturbations into the part that only has support from k less than lambda, so a large wavelength part and a small scale part. And then we want to keep the modes explicitly that are below the cutoff, but integrate out all the modes that are above the cutoff. And integrating out is what high energy physicists say, statisticians say marginalize over, right? It's the same. It's precisely the same thing. So what happens when you integrate out these small scale modes? First of all, you're forced to introduce bias terms that encode the dependence of the galaxy density field on large scale perturbations, right? The galaxy density field, of course, knows about all the small scale stuff and how the small scale modes couple to large scale modes. And there's a precise set of terms that are allowed for how this coupling can look like, and those are the ones that we keep. And in this case, these bias terms, for example, density itself, density squared, tidal field squared, and so on, are all constructed from the filtered field, right? Because we don't want any modes above the cutoff. And then of course, the small scale perturbations are there, right? We cannot simply ignore them. For us, what they do is they add noise, right? We cannot describe them deterministically in terms of the delta lambda. They are a noise term. So we just add an additive noise term. So obviously, many of you know that I could lecture for hours on bias. Let me just briefly say in one slide that there's a well-defined approach to constructing all the relevant bias terms at a given order in perturbations and in spatial derivatives. And basically what we're doing is we allow for the galaxy density to depend on the density and tidal field along the entire past trajectory. So we include the fact that galaxies don't form instantaneously. But again, so there are no coefficients in front of the displacement, new coefficients in front of these displacement terms I mentioned earlier. So this already fully incorporates the constraints from the equivalence principle. That's actually one way of constructing these bias terms. So the noise is actually, or stochasticity is actually very interesting. It's, this whole likelihood approach gives a very different perspective on this noise. But basically, physically, how it arises is it's due to a superposition of many small scale modes, but a superposition that's localized in real space because galaxy formation happens on small scales, right? So from this fact, several interesting properties follow. The first is that because it's a superposition of many modes, we can invoke the central limit theorem, and this noise becomes approximately Gaussian distributed. And in particular, the lower the wave number you're looking at, the more modes superimposed to form that, and the more Gaussian it is. Okay. And the second, the locality in real space, manifests in the fact that on large scales, at low k, the power spectrum is a white noise power spectrum, and with corrections that go as k squared. contact terms in field theory. Right. So this was, I mean, a more detailed derivation with connection to field theory is found in this paper, which yeah, I wish I could talk about in more detail, but it's impossible to cover everything. So for the likelihood, these properties are really central because they actually allow us to integrate out the noise analytically. Again, the noise, right? It comes from the small scale mode, so it has very high dimension. But fortunately, because of its properties at low k, we can integrate it out up to some lambda, and the result is this. I mean, it looks worse than it is. It's just a multivariate diagonal likelihood, Gaussian likelihood in Fourier space, where now we're comparing the observed galaxy density field with a field that I call delta G det, and that's just the sum over, that's sort of the mean field prediction. That's for the mode of the likelihood. That's just the sum over bias coefficients times these bias operators. And then with a constant noise amplitude on large scales. Okay, so this is really a very simple likelihood, and the only subtlety is here that we sum up to some maximum wave number, lambda, right? Because we have this cutoff. An equivalent formulation exists in real space because you could, by Parseval's theorem, you can transform this to real space. The nice thing about this approach is that here it's very easy to go to higher orders, right? So several of you have done computations in large-scale structure perturbation theory where you calculate the 1-loop or 2-loop power spectrum, say. It's very, very complicated, especially bispectrum. It gets very complicated if you want to go to higher orders. Here, we just add more bias terms, right? That's all there is to it. And in general, you want to also modify the noise. But so it's really very simple to go to higher orders, and I will show some results on that. But what's even more, well, maybe equally important, is that if you look carefully here, the bias coefficients only enter quadratically in the likelihood, right? So that means the likelihood is a quadratic function in the exponential of the BO, and that means I can analytically marginalize over the bias parameters. So I do not have to sample them anymore. They are basically, the likelihood becomes a bit more complicated, but it's now a function only of this sigma naught and cosmology. So that makes it very nice because we're really reducing the dimensionality of the parameter space. And as it should be for an EFT-derived object, there is a clear relative ordering of the various bias and stochastic terms. So this is only the leading order. There's also, the noise in general is modulated by large-scale perturbations. It can also be non-Gaussian. And there's a rigorous ordering, relative ordering of these terms. So you always know what you need to include next. Again, referring to the same paper. Okay, so this is, maybe if there's any questions at this point, I can take them, although I don't see anything, so someone has to manage this.
Okay, thanks for sticking to time very well. In fact, you had another couple of minutes because we started late.
Oh yeah, sorry, I was just asking for intermediate.
Oh, okay.
So how much time do I have actually?
About another 5 minutes or so, if that's
okay.
Yeah.
Yes, so now I just wanted to show some results on this. So basically, very briefly, this is a toy setup where I look at halos in n-body simulations as my mock galaxies. And if I have an n-body simulation, I know what the true initial conditions are, right? And so I can actually, I don't need to even sample the initial conditions, and that reduces the dimensionality of the problem and makes it very easily tractable to the extent that even I can write a code that does that. So, and then we can do what's called a profile likelihood to get cosmology constraints, in this case, sigma 8. So basically, I just want to see, does this whole thing work? Does my likelihood recover correct cosmology? And the interesting point to note here is that, again, there's a degeneracy between amplitude and bias at linear order. So this really comes from nonlinear information. This plot shows basically 1 is unbiased, so unbiased sigma 8 inference for 2 different simulation realizations, 1 specific halo sample as a function of cutoff. And you can see here that it works to sub% for a specific, in this case, 3 LPT. And just to illustrate that it's easy to go to a higher order, I went up to 5 LPT with a 5th order bias expansion. Here we're talking about more than 30 bias parameters, I think around 40 bias parameters. But because they're analytically marginalized over, it's tractable. And this is a different representation now, plotting different halo samples in one plot, but at a fixed cutoff. And you can see, we recover sigma 8 correctly to within about 1% with a statistical error bar of order 0.5%. So this is, seems to all work and have extremely small error bars. So the one burning question then, of course, is what remains of this once we sample the initial conditions. And I just wanted to flash some very preliminary results. I mean, we now have this EFT likelihood implemented in the full HMC Bohr code developed by Jens Jasche and Guillaume Lavaux. And now just testing it on a sample that's generated from the likelihood itself. And so this is a snapshot of the chain. This is a histogram of sigma 8. Basically, I just want to highlight 2 things. The first thing is you see very long correlation lengths. So it's a bit painful, and clearly we need to understand better how to do the sampling more efficiently. But the second point is that, as expected, this is really just a code test. The true value is well within the posterior, and we get a width of order 5%. For this volume and effective number density, this is comparable to the linear constraints you would get from RSD on F sigma 8, but it's based on nonlinear information. Okay, so think about this. We have something that is only accessible by nonlinear information, but we get an error bar that's comparable to that of something that is measurable using the linear redshift space power spectrum. So I hope that is at least some good evidence that there's much more information in large scale structure than what we've been extracting so far, and rigorously controlled information at that. Again, this is with a cutoff of 0.1, right? So this is not trying to go to really small scales. So yeah, let me just leave this basic summary here and take questions. Thanks.
Okay, thanks very much, Fabian, for a very interesting talk. I see lots of questions coming up. What about Blake? Do you want to ask a question?
Yeah, Fabian, thanks for the nice talk. I was just wondering, given that you have a cutoff, do you have a sense for how much information you'll gain beyond combining power spectrum and bispectrum analyses, for example, or power spectrum, bispectrum, and trispectrum? Do you think, given your cutoff, there's information that's not captured in the leading moments that you would get?
Yeah, that's an excellent question. And we definitely plan to address that eventually. It's a little tricky to well, I mean, it's certainly possible to just measure the bispectrum using in the same setup and then do that comparison. But you have to be honest, right? You have to include the proper covariance of the power spectrum and biospectrum. Because here, the covariance, of course, that's one nice thing, is that there's no covariance, right? It's all built in. So yeah, I mean, that comparison will be definitely very interesting. It's not straightforward. I mean, you really have to do the computation, I think.
So my question is a little bit naive. I mean, you're planning on incorporating the bispectrum into your forward modeling methods.
No, so there's two things. I mean, you can do forward modeling on summary statistics. So you first compress the data and then you do a forward modeling approach to compute the theory prediction. That's another story. So here, there is no bispectrum, right? We compare the entire galaxy density field.
Yeah.
So there's nothing else to do. If this works, in principle, there's nothing else to do. I mean, it gets all the information of the modes up to lambda.
Nico, do you want to?
Yeah, can I ask a question?
Sure.
That's very exciting. I was wondering, since you're testing this on a halo catalog, there's more information than just the density field of halos. You could also include, for example, the masses of the halos. Have you thought about that?
Thought about it for sure. So in general, more generally, one could think of splitting the halo sample into many mass bins, right? And then analyzing them as a multi-tracer. And while I'm on the slide, it's very easy to see how you would generalize this to multi-tracer, right? You would allow each tracer to have independent bias parameters, and then this shot noise will become a shot noise covariance between different samples. And that's absolutely doable. I've done some first tests, but not enough to conclude anything. So yeah, absolutely. I think if there is multi-tracer information out there, then this is a very nice way to get at it, because again, it's fairly straightforward to put it in.
Thanks. Any other questions? Did I see Oliver's hand? Or
Paul, there are two questions in the chat from Cora and George.
Okay. Am I meant to read them out, or is Cora here? Cora.
I'm here. Hi, Fabian.
Okay.
So I was wondering, you said everything should be independent of the choice of the cutoff. What about the shape of the cutoff? Like if we cut in K-space, real space, have weird filters there?
Yes, so that's a good question. So from a theory perspective, it's much nicer to cut in K-space. So that's where it's well defined, and you. One example of this is the fact that the noise has this nice property in Fourier space, right? It does not have corresponding nice property in real space. So we just know that in real space, the noise correlation function is limited to small scales, but we don't know what the shape of it is. In Fourier space, we know that it's just a constant on large scales. So in general, one could repeat the derivation with maybe a Gaussian cutoff or something like that. Again, I think it should not matter, but this would be an interesting thing to look at for sure.
What about George?
Well, it's a bit of a trivial question. The posteriors that you got on Sigma 8 had a dip in the middle, and I was wondering whether there was anything in that.
Yeah, right. Actually, of course, initially I thought, should I really show this because of that? But then I thought, I mean, it's always good to be honest. So this is, again, you can see so this is the chain itself, right? And so you can see a lot of correlations here. So the dip is because initially there were a lot of samples up here, then for a while it was down here. And so there were very few samples in the middle. Now towards the end, it looks like it might be filling up the middle. Eventually it should fill up the middle. But
so you can stop there now. Sorry.
Yeah, so it's we just have to be very patient at this point.
It's a sampling issue.
Yes, yes.
Okay.
Sorry, may I? Guadalupe Cañas in here. Thank you so much for your talk. I found it very interesting. So a question related to this. Can you repeat what was the sampling method that you were using? I think that you mentioned Hamiltonian Monte Carlo.
Yes.
Why did you decide to use this sampling algorithm at the beginning and not going for something more general?
Well, so okay, so there is So for the phases, so for the actual initial density field, it uses Hamiltonian Monte Carlo. And the thing is that so imagine you have a 10 million dimensional parameter space, right? So the classic MCMC method would be to take a random step in a random direction, right? The likelihood that you hit the point where the likelihood actually increases in a 10 million dimension parameter space is, exponentially small. So HMC allows you to systematically follow the gradient of the likelihood to regions where that are preferred, and to basically explore much greater regions of parameter space efficiently. So basically, in general, you want a sampling method that works in extremely high dimensional parameter spaces. So HMC is excellent for that if you know how to tune it. And Guillaume and Jens have put a lot of work into that tuning. That's the basic idea.
Okay, we should be winding up, but I see a couple more questions. Dan Meerberg, are you quick questions? Yeah.
Do you hear me? Yeah, it's a pretty quick
Yeah.
question, I think. Very nice talk, Fabian. So one thing that got lost on me, so you said this only contains nonlinear information, but shouldn't it also contain some linear information? I mean, you're combining all the information, right, in this likelihood approach. So that I didn't quite understand.
Yeah, sorry. I mean, it was probably maybe not very clear. So in general, absolutely, the likelihood also uses linear information. The thing is that I am using halos in real space, and B1, the linear bias is free, right? I don't have any prior on that. So that means at linear order, B1 and sigma 8 are exactly degenerate. So I do not have any information. And that's what I mean, this is nonlinear information.
I see. Otherwise, you wouldn't have any constraint to begin with.
Right, exactly. This is kind of a lingo I developed. Maybe I should really define this more. Yeah.
Okay, so last quick question, Lam Hui. Yeah.
Hi, Fabian. I have thanks for the talk. I have just a relatively quick question. In the power spectrum for epsilon, what you call epsilon, do you set it to be 1 over the number density, or you actually allow that to be free?
Excellent question. Yes, we allow it to be free because it's in the EFT, it's a free coefficient. And the 1 over n bar is the Poisson prediction, but we know that, if you construct these bias terms, these nonlinear bias terms, there will be corrections to the noise amplitude. So we cannot set it to 1 over n bar. So we leave it free, yes.
I see. And you allow it to have a uniform prior on the
yes.
On the amplitude. Okay.
Right.
Thanks.
Okay, well, I think we'd better finish there. Thank you very much, Fabian, for this very nice overview.